In section 2.7, we will learn some useful information inequalities which are implied by the basic inequalities we learned in the last section. Theorem 2.38 says that conditioning does not increase entropy. Specifically, entropy of y given x is always less than or equal to entropy of y, with equality if and only if x and y are independent. Intuitively, this is the meaning of this theorem. Suppose we are interested in a random variable y with a certain amount of uncertainty. Then, by knowing some sign information x, the amount of uncertainty about y can only be decreased. When x and y are independent, knowing x will tell you nothing about y, and therefore, the conditional entropy of y given x is exactly equal to the entropy of y. The proof is very simple. Consider entropy of y given x equals entropy of y minus mutual information of x and y, which is less than or equal to entropy of y, because the mutual information between x and y is always bigger than or equal to 0. Equality holds if and only if the mutual information between x and y is equal to 0, or x and y are independent. Similarly, conditioning on an extra random variable z, we have entropy of y given xz is less than or equal to entropy of y given z. So we have shown that conditioning does not increase entropy. However, conditioning may increase mutual information, as we will see later in this course. Therefore, in general, the inequality ixy given z less than or equal to ixy does not hold. Theorem 2.39 is called the independence bound for entropy. It says that the joint entropy of x1, x2 up to xn is less than or equal to the sum of all the individual entropies, namely summation I from 1 up to n, entropy of xi, with equality if and only if xi, I from 1 up to n, are mutually independent. We now prove this theorem. First, by means of the chain rule for entropy, we write entropy of x1, x2 up to xn as summation I from 1 up to n, entropy xi given x1 all the way to xi minus 1. This is less than or equal to summation I from 1 up to n, entropy of xi, because conditioning does not increase entropy. Now the inequality is tight if and only if it is tight for each I. That is, entropy of xi given x1 all the way to xi minus 1 is equal to entropy xi for I from 1 up to n. This is equivalent to xi being independent of x1, x2 up to xi minus 1 for each I. Then, the joint probability of x1, x2 up to xn can be written as px1, x2 up to xn minus 1 times pxn, because x1, x2 up to xn minus 1 is independent of xn. In the same way, we can write px1, x2 up to xn minus 1 as px1, x2 up to xn minus 2 times pxn minus 1. So finally, we have px1 times px2 all the way to pxn. For all x1, x2 up to xn, that is, the random variables x1, x2 up to xn are mutually independent. Theorem 2.40 says that the mutual information between x and y, z, is bigger than or equal to the mutual information between x and y, with equality if and only if x, y, z forms a Markov chain. The proof is straightforward. By the chain rule for mutual information, we have ixy z is equal to ixy plus iz given y, which is bigger than or equal to ixy, because Ixz given y is always non-negative. The above inequality is tight if and only if Ixz given y is equal to 0 or xyz forms a Markov chain. The next lemma says that if xyz forms a Markov chain, then Ixz is less than or equal to Ixy and Ixz is less than or equal to Iyz. In other words, if the random variables are closer on the Markov chain, then they have higher mutual information. Let us now prove lemma 2.41. First, assume that xyz forms a Markov chain, that is, x is independent of z given y. Then, Ixz given y is equal to 0. To prove 1, consider Ixz equals Ixyz minus Ixy given z. This is an application of the chain rule for mutual information in reverse order. Consider I, x, y, and z equals Ixz plus Ixy given z. This implies Ixz equals Ix and yz minus Ixy given z. Now this is less than or equal to Ix, y, and z because Ixy given z is always non-negative. And this is equal to Ixy plus Ixz given y. And this step is just another application of the chain rule for mutual information, namely Ix, y, and z is equal to Ixy plus Ixz given y. And this is equal to Ixy because in step 1 we have seen that Ixz given y is equal to 0. Since xyz forming a Markov chain is equivalent to zyx forming a Markov chain, we also have proved 2 by symmetry. A corollary of lemma 2.41 says the following. If xyz forms a Markov chain, then entropy of x given z is greater than or equal to entropy of x given y. This is so because on the Markov chain, y is closer to x than z. Here is the proof. Consider entropy of x given z equals entropy of x minus mutual information between x and z. This is greater than or equal to entropy of x minus mutual information between x and y because of lemma 2.41. Then, entropy of x minus mutual information between x and y is equal to entropy of x given y, and this proves the corollary. Here is a remark. Suppose y is an observation of x. Then the corollary says that further processing of y can only increase the uncertainty about x on the average. The next theorem is a very important result called the data processing theorem. It says that if u, x, y, and v forms a Markov chain, then IUV is less than or equal to Ixy. We now prove theorem 2.42. Assume the Markov chain u, x, y, and v. Then we have the Markov subchain u, x, y, and the Markov subchain u, y, v. From the Markov chain in 1 and lemma 2.41, we have the mutual information between u and y is less than or equal to the mutual information between x and y. Similarly, from the Markov chain in 2, we have the mutual information between u and v less than or equal to the mutual information between u and y. Combining these two inequalities, we have IUV less than or equal to IUY and IUY less than or equal to IXY. Thus, we have proved that IUV is less than or equal to IXY. Therefore, the theorem is proved.